Professor Aaron Quigley is the Science Director and Deputy Director of CSIRO's Data 61. Professor Quigley will delve into a range of novel interactions which are supported by new forms of sensing on mobile and wearable devices. So this is IoT all over the things. I'd like to introduce Professor Aaron Quigley. Oh, he was like, oh shit. Sorry for that, mate.
That's all right. Thank you very much. Thank you. Thank you very much for having me. It's always lovely to come to new conferences. It's a treat to meet new people. Very active discussion about spaces versus tabs last night. That was keeping a lot of people in furore. One thing I just wanted to explain is that there's a lot of people I want to say thank you to for the work that I'm going to be talking about today. I've worked in academia and industry in different countries in Scotland and Germany, Japan, Singapore, Ireland, the USA, and here in Australia a number of times. So I've had sort of one academic track working through the university sector, most recently as the head of school in UNSW in Sydney, but also I worked in industry in semantic designs, Mitsubishi Electric, visiting scientist with IBM, and most recently the director of the Scottish Informatics and Computer Science Alliance in Scotland. And all of those things have brought me to CSIRO, where I am today. If you doze off, I will be paying attention. So if I see heads dropping, I just want to tell you up front that the thing you have to try to remember is that as new devices emerge, whatever it is, be they embedded in the environment, be they things that you carry, be they ingestible, be they wearable, every type of new device, you can think about the sensing that it has for its primary purpose, but then often there's secondary things that you can do with these sensors that you hadn't necessarily thought of before. So somebody might introduce a pair of eye tracking glasses for one purpose, but then actually if you think about what the sensors are actually doing and what they're capable of, you can actually start repurposing them for doing all kinds of different things. And then when you have multiple devices like this, you can actually start triangulating these devices and doing new forms of input. So that's the main take-home message, is that look at the devices that you have around you, and every time you get something new, think about, is there a way to mash it up with the other devices you have and the sensing capabilities they have to do new things. And with that, you can adapt to changing human attention, changing levels of human vision. You can even think about supporting people with low or no vision, so that there's all kinds of accessibility potentials with some of these devices. So what I'm going to talk about today is some of the work that we've done on sort of traditional devices like fixed computing, laptops, tablets, but then also with mobile devices. Sometimes they might be wrist-worn, sometimes they might be things in your hand. Some of our more recent work on shoes and contact-based sensing, but then also things with face masks and eyeglasses. So lots of different types of places where you can actually do sensing. And each of these types of sensors we're using the sensors that are embedded in these devices in non-traditional ways. They're not intended for the uses that we're putting them to, but we're repurposing them and giving them an extra life to do new things. So way back when we started on a lot of this work, it was at the time where multiple monitors and multi-displays were starting to become much more commonplace. And what we started to realize is that as you start looking at these environments, that you have lots of screen real estate opening up, but our attention and our degree of being able to keep track of all of these things is limited. So our attention is limited, and we only have two eyes individually, or one in some cases, or none if we have no vision. And we have to kind of accommodate for all of these things. So one of the earliest bits of work is we started using cameras that were embedded in multiple monitor situations. And all we were doing was just keeping track of, were you paying attention to the display or not paying attention to the display? And when you were not paying attention to the display, we basically froze the display, buffered all of the content, and then squeezed it down so that when your attention returned to that display, this diff displays, we would actually show you the diff between what was there and what was there now. And the idea was so that you didn't miss anything, even though your eyes weren't currently actually fixated on that display. And we extended that up to being more than just small monitors. We actually extended it up to even larger monitors. And in this, we actually explored different types of differential screen updates. So sometimes it might be a pixel map where we're just mashing all the pixels that have changed over time into a visualization. But sometimes it was an aura, so the windows that were actually on screen, they were showing a small aura of information to say, well, this is a part of the screen that actually changed since you were last paying attention to it. We extended that up to looking at things like spider eyes, which wasn't designed for an individual. It was designed for groups of people interacting with large displays. So if you were working separately, you would see two displays, but as you came together, it would merge the displays. And the idea here is that as you start getting these larger and larger display environments, how do you accommodate for human attention, and how do you actually take advantage of the fact that you've got multiple people interacting with these displays at a distance? One of the things we did was we took that sort of aura concept, which is on a window basis, and we brought it down into an individual widget. So this is something that was actually built into a widget toolkit that was used in the user interface design. So each individual widget now knew, have I changed my content since the user was last paying attention to this display? So you can imagine large displays, multiple monitors, applications that are spread across a large amount of real estate. One particular widget might have content that's changed, and you could easily miss it. So we built this into a user interface toolkit and then just recompiled applications with this new interface toolkit, these widgets in it, and then actually ran different experiments. One of the experiments was a ubiquitous health application that was designed for hospital monitoring. So here you kind of got a standard setup with, three monitors, patient records, calendaring, room allocation, some location information about where patients and doctors currently are, some on-call information. And you can imagine this spread across multiple screens, and it would be very easy for you to miss an update. Something might change, there might be an alert, there might be something that actually happens. Now, if you want to rebuild the entire system to accommodate for this, you would have to do a lot of recoding. But with our approach, all you need to do is just recompile with the new widget library with our hardware installed, and then you actually got this type of tracking built in. And what we did, we were able to show in our experiments that without the toolkit, people were missing a lot of these updates. So the red bars are the things that people were missing. But with the toolkit installed, to actually give people alerts as to which widgets were actually changing, people's attention and ability to spot those, the accuracy increased quite dramatically. So that sort of tracking and having cameras to look out at people sort of inspired a whole body of different work that we actually started doing. One of which was the realization that when things are changing, people don't necessarily see the changes. So there's different reasons for why people don't see changes when they're looking at displays. Sometimes it might be traditional, what is classified as change blindness. Sometimes it might be inattention blindness. So how many of you ever seen the basketball players and the gorilla experiment? Yeah, okay, so you've seen change blindness, okay? That's inattention blindness, okay? That's actually not change blindness. Change blindness is, as you'll see in a second, a different visual phenomena. Inattention blindness is where you're paying attention to one phenomena and a different phenomena is occurring, and you're not thinking about that second phenomena, so you don't actually see it. So here what we were doing was we were trying to design distance-based interaction so that as your arm is extended out to a great distance, the interface would simplify to, let's say, for navigation, just be an arrow. And as you started bringing your device closer, we would start introducing more and more content. So at the closest resolution, you would actually see labels, text, other things like that. And at the middle distance, those details would fade away. And at the greatest distance, it would just translate into a different type of interface entirely. So this was the proximity that we were actually using. And then the interface would adapt accordingly. It would change depending on the distance. So arm extended, middle distance, and close to the face. The question is, if you're moving between those two displays, will the user perceive a change? When it's that dramatic of an interface, they will. But what about in this case? Will they actually detect a change when they're moving between one map layout and a second map layout, and all you're doing is adding and removing small amounts of content like labels or color information or some other map details? Here is a type of change blindness experiment that people use. And the question is, do you see the change? And if you look at the screen, you should all see the change. There should be nobody who doesn't see the change if you're looking up, if you're not looking at your laptops or phones. Okay, does anybody not see the change? Nope, we're all good. So we can all see the bag appearing and disappearing. What we'll now do is the mud splat test, which is imagine an image, a visual disturbance, and then a second visual image. So here you've got image 1, a flicker, and image 2. Suddenly, seeing the change is much harder. So you can put up your hand if you can see the change. We've got 5, 6, 10 people, 12, 14, 15. The engine under the plane. Oh, no, me taking advantage of them. And if I can do that without it feeling like me tricking you, then maybe I could do different things. So could I actually take into account the proximity that the display is to your face? Can I adjust the content on the interface? And then I take advantage of the fact that we know how change blindness works and actually build interfaces that adapt accordingly. And that's what we did. So here we took an experiment where we asked a user to move the display backwards and forwards, measuring the distance, and then we were changing different visual components of the display and then experimenting to see what they did and didn't actually see. So now in that case, did you see the change? You probably didn't, because it was quite slow. So here, watch again, and you'll see what actually changed as the user was moving the display away from their face. So this green colored region basically fades out as they move the display away. So you can see they move it away, and then we ask them at the end of the experiment, did you see a change? And you can change big amounts of information on screen. You can change labels, big regions, you can add and remove lines, you can do all kinds of things, and people just will not perceive them because of the way we know the visual system works with change blindness. We did an experiment. This is what we do in academia. Lots of, I heard some people at your conference berating the academic publications for being unimplementable. We try to make them implementable. We try to write them up in a way that other people can take what we've done and reproduce them. And if we don't do that, let us know. Don't just say like, oh, that's unimplementable, because chances are the academics or whoever's written the research paper has content, code, data sets, and we now try to publish as much of that as we can. The ACM encourages that. Lots of other publication venues do that as well. So we want to try to get it out there so people can actually implement it. Anyway, the error rates were quite high when it was a gradual change. When it was an instant change, people actually saw it better. And when there was no change, people there was a very low error rate on that. Instant change causes a change in the threshold, this visual disturbance, but with the gradual change, the visual disturbance isn't sufficiently high for users to be able to see it. So this sort of work of paying attention to human capabilities and actually adapting interfaces is something that we've done lots of to try to give the interface more intelligence without necessarily just relying on kind of stock standard AI techniques. Now, when we were doing this devices looking at the face, we actually then started exploring the devices, not just looking at the face, but actually looking at the physical environment around you. So one thing we started looking at and we started discovering is just when people are not interacting with their devices, they either keep them in a purse, a pocket, on the table, and sometimes if it's on a table, it's face up, and sometimes it's face down, depending on the context. So we explored both the face up and the face down context. So we've discovered through our surveys that roughly 50% of people keep their devices like this and 50% of people keep their devices like this. And what we wanted to do is to be able to use those situations to actually see if the phone could understand more about the context of the environment that it was in. So we designed and invented this technique called spec cam. And with spec cam, we use the front-facing screen of the phone as a multispectral light source, and then we use the reflected information to basically train a machine learning system, either scalable vector machines or other forms of neural networks to actually recognize the content. Let me just turn this audio off. So what's happening is the phone is placed on different surfaces. There's a bumper case that raises it slightly away from the surface. The light is reflected from the screen. So the light is emitted from the screen, reflected off the surface, and then bounces into the camera at the front. And what you end up seeing are the images on the left. So they're very blurry images. There's not a lot of detail in there. When there's a very distinctive surface characteristic, like the tile, for example, you actually get more graded images that are coming up. But in other cases, you don't get that much information. But what you can do with this is, that's the test rig, there's the bumper case around it. What you get back are this set of images on the left. From that, you can extract histograms, some intensity information. You can do a gradient detection algorithm on it, figuring out what you're actually looking at. And then you can use that to train a machine learning system. So here's our data set of different types of objects: wood, cardboard, different types of book surfaces. What's quite interesting in this is even things that look quite, to the human eye, look quite visually similar, like ceramic versus porcelain plates, actually have enough different characteristics in them for us to be able to pick up the differences in the experiments that we were actually running. So these are, and things like breadboards, that's where you can probably see the clearest example of the type of surface reflections that you're actually getting. We used different types of phones with different types of light sources. The Galaxy S6, the OLED, was giving us quite a clean light signal, and you can see what's actually being reflected back across the different types of objects there. When you do these types of experiments, we're very keen on trying to come up with experimental data sets so that other people can take it and then build on this research. So we're exploring different types of colors, different types of material. We also want to have a ground truth. That's often very difficult in human-computer interaction to determine what is the ground truth. But in this case, since we were looking at color, we actually were able to use a spectrometer to give us a ground truth. And as you'll see on the next slides, the spectrometer actually doesn't work as well as this approach. And the reason for that is the spectrometer is looking at a point source of light. It's looking at a very small region of the object, whereas this is illuminating a much larger region, so you're getting more detail coming through. We tried different multispectral light sources, and then we broke the color channels into 64 bins for doing the analysis. So some of the experiments were taking printed material, different colors, different saturation brightness levels, trying different random positions, trying different variations of support vector machines, and then we were able to show the spectrometer was getting an accuracy of 82%, but SpecCam was getting 88% in those experiments. So then we wanted to test outside of the dominant ranges, so different hues. And then again, we ran another set of experiments where the accuracy was lower, but then you're looking at a much larger set of colors. And then we increased the degrees of difference in the colors that we were experimenting with, and again, the accuracy went up. The scenarios here are, today, mobile devices have a good sense of their accuracy either through GPS or through assisted GPS or through sometimes indoor location awareness with Wi-Fi signaling, occasionally using Bluetooth for doing the determination. Some types of mobile devices actually have ultra-wideband sensing in them. But what happens when you're down into a room or you're down into a small scale and you actually want the device to know which particular surface it's on to actually start triggering new forms of interaction? And that was the motivation for why we wanted to have SpecCam. So these are just some of the results. These are different ways of doing machine learning experiments. Leave one out, tenfold cross-validation, just two different approaches, and you can see the accuracies there. A very large thing that now happens in machine learning, especially with respect to intelligent user interfaces, are these confusion matrices, and we try to analyze a lot of the systems and a lot of the ways of our working with these confusion matrices. So we try to see if I train a system with lots of data and then I actually try to re-recognize particular objects, how accurate does it recognize the correct object versus, or the correct type versus the other types? And as you can see here, anything that's in gray, those are errors. So you can see on the left, there's some errors there, but then with 4 colors differences, you can see the error rate actually starts to go down, so the accuracy increases quite a lot. That's not a huge data set. You're only talking like 30 objects in that particular case, and you can download the data set if you'd like to try this out yourself. Now, because we had the bumper case, we have a very controlled environment, so that's not necessarily always as realistic as you would imagine. Very stable data collection, there's no light leaking from the outside. That's why we get such a high accuracy. But of course, we're getting very overexposed image, and we have to then deal with the dynamic exposure setting as a result. Some of the problems here is that it's surface only. You're only looking at the object surface. We also had to use the built-in magnetometer. That was to allow us to determine whether or not it was a solid metal or a plastic, let's say we were studying. Allowed us to differentiate between those different object types. And then you could actually imagine combining this with, let's say, radar or terahertz imaging. And then maybe you'd get a wider range of objects, let's say natural flat types of scenarios. And we were trying different types of screens, different OLEDs and things like that. But one of the challenges even though it was an interesting use case for us, there's people placing their devices down beside their bed, at coffee shops, in bags, in their pants pockets, in different locations on their body and different things like that. That only accommodated for 50% of the users. There's 50% of people who actually don't do that. They actually place their device the other way around. So what about them? Well, for those people, we decided we'd do a different experiment. We'd try a different way of doing this. And we invented a system which we only published last year called microcam. Because the hardware is changing all the time that's coming out on these devices. So when we started doing some of those very early distance-based studies, these devices did not have front-facing cameras. Hopefully none of you are young enough not to realize that that was the case, that these mobile devices used to not have front-facing cameras. But there was a time when they came out, they had no cameras. Remember that? Then they had a back camera, then they had a back camera and a front camera. It's changing all the time. Like, these devices are adding new types of cameras and new types of sensing all the time. So with microcam, some new forms of mobile device are coming out with microscope cameras that are actually embedded into them. So what we can do in that case is we can process those microscope images. We can use MobileNet, which is a form of neural network. And then we can use it for doing two things, not just for doing object recognition or prediction. We can also use it for doing material recognition and prediction. So traditional cameras, if you place them down, the lens just gets blocked. There's no light coming in. It's too close. It can't focus, and you're not seeing any image. And that's what we had up until recently. But with microscope cameras, as you place them down, the microscope lens actually starts to kick in, and you actually get an image that's actually recorded off of the surface. Now with that, there's one device called the Oppo X3 Find Pro. With that, we can then start doing contact surface sensing. We can look at the surface texture, and we can actually use, if we don't have that, we can use a clip-on camera if we don't actually have mobile devices that actually have a micro camera built into them. And the motivation for this is to start actually understanding where your mobile devices are going to be. Are they on desks, and then sofas, cabinets, beds, counters, sinks? Knowing exactly where they are and then using that for placement awareness or bookmarking or triggering different things to actually happen, like playing music or playing different types of interactions. So this is one of those sort of fine-grained material ubiquitous computing scenarios. It gives you positioning. You can start doing gesture estimation, motion detection, identification. So you can start determining where the mobile device is and then actually supporting different types of applications. So you can see here, we started collecting data in different contexts, exploring what we would actually do. We use this Oppo X3. We also explored some of these clip-on cameras, but we found the Oppo was the best approach here. So Huawei starts having some of these devices start being built in. So the placement-aware computing is a fairly simple concept. Like, you want to bookmark certain locations. So let's say, for example, you're listening to an audiobook and you want to listen to that audiobook when you go to bed. Instead of having to hunt through, find the application, just say, when I place my phone on my nightstand, that's when I want the audio book to start playing, and I want certain other features to actually be set. Or when I place my phone beside my computer at work, I want something else to actually happen. So places, physical locations that are around you, become places for triggering particular types of interaction. At the moment, you don't have that. At the moment, you place a device and the phone knows nothing about where it physically is, but now the place can actually be a way of interacting with your digital ecosystem. You can also start using your body for triggering shortcuts, because you can start recognizing different skin types, different types of material, different locations on your body, and then using that to trigger. Let's say you put the phone into your pocket for running, or you put it into a side pocket for walking. Different things can actually trigger depending on the body location of the device. For the longest time, we've been very keen on trying to, you'll see in the next OmniSense, we've been very keen on trying to use the back of the device. We've got the front of the device pretty locked down. Lots of things there, cameras, touch screens, voice input. Like, there's lots and lots of activity focused on the front. But what about the back of the device? Like, why not use that for interaction, for swiping, or for gesturing, or for tapping, or for notifications? It's a very neglected part of the device when you actually think about it. Likewise, the sides, to the point where people now actually do types of interactions where they squeeze the device, and you actually get squeezable interfaces. There's a huge amount of research in this area. Anyway, we're using it for doing fingerprint swiping. An interesting thing with the microscope is that you can actually start doing things that are beyond what the human eye can actually see. So you can actually start embedding hidden tags. In this case, we were exploring QR codes that were actually printed inside of objects that you just couldn't see, and then using that to trigger, let's say, URLs opening, or even putting in things like micro watermarking into the objects around you. A large group of people are very keen on trying to explore what happens when these devices can just kind of blend into the background. So even thinking of them like to being able to kind of camouflage themselves as you place them on the surface, then triggering particular camouflage. Again, we use the SpecCam data set again, but then we also extended it and added in new data sets, new types of objects, new types of materials. Again, similar sorts of experiments to actually see. And again, all that data set is available if you want to try and build or extend this type of work. It's a fairly simple pipeline. First of all, you use one type of sensor to determine whether once the phone is stable, you then take the raw microscope image, you process that, you then split it across two neural networks, one for doing object recognition, one for doing material recognition, and then once you recognize it, you then do the mapping relationship. Once you know what the object or the material is, that then becomes a piece of input for different applications to be able to use it for driving particular types of interactions. There's also this continual learning. I won't go into that. And there's some experiments there where it works quite well. Cross-validation. So I'll skip all this. Okay. So this sort of kicked off a whole bag of research. So we tried using the front-facing camera and the screen for downward-facing interaction. We tried to use the back-facing microscope camera for front-facing interaction. Then 360 cameras started becoming more prevalent. They started becoming available on handheld GoPro type devices, pluggable modules that you could put into phones. And then smartphones started coming out with these 360 cameras built into them. Once we had that, we actually decided we'd unify all of this work that we'd actually been trying to do, and lots of other people have been trying to do in different ways, and built this OmniSense type of sensing. So with that, what we now can do is, when you pick up a device, we can tell whether or not it's your left or your right hand that's gripping the device, which can be very useful for people who are left-handed versus right-handed for, let's say, keyboard input, or even for some of the gesture inputs that these systems have. We can also actually start to use the back of the device for tapping, because suddenly we can actually start tracking your fingers on the back of the device. We can actually also look down at your legs, and you could even start using your legs for doing gestures, for doing inputs to systems. We can actually recognize the two hands that are gripping the device and where they're gripping the device. We can actually also detect where the finger is on or above the device at the front or at the back, and use that as a form of distance. Of course, we can use our body proximity as we had previously. We can use left or right thumb hovers. We can even track your front body motion and your facing. You're touching your face. But because it's a 360 camera and that's actually looking at the environment, we can do much more than that. We can also use it for doing, let's say, danger detection. We can also do other types of context sensing. We can look at other people interacting around you. Even if you have a pen and you want to use a stylus, you can actually just track a regular pencil and then have it being used as a stylus for this type of input. Tracking your body, your face. You can even use it for generating virtual avatars. And you can even have sort of tabletop or in-car interactions. All these become possible. Let me just play this. Hopefully it plays. Yeah. So you can see it has this very large 360 volume video information. So first of all, you can then start tracking the body. So you can start to see how it's recognizing where the legs are, where the arms are, where the fingers are. Here you're just seeing like the 360 video being used for it. Here it's using your legs for actually inputting and playing a game as you're standing. Here you're using the distance to actually control the map. You're using the angle to control what you're seeing with the map. Here it's just showing you some affect recognition. The design space is the upper body, the hands, the lower body, the environment around you. It's then actually looking at on the device, so where you're physically touching the device, so touching the back of the screen, touching the front, touching the sides. around the device within sort of close proximity, where it's kind of a zone around the device, and then at a distance. So you imagine other people in the environment around you, cars, other objects that actually are coming on or near you. So this work, which is kind of like a culmination of 10 years of work that we've done, brings all of the different types of sensing at a distance on and around the body together into one type of sensor. And again, also one type of sensing that you can actually use for doing this type of context awareness. I'll skip over that. So here you can see the type of tracking that you're getting, the handedness, adaptive. An interesting one, which I wouldn't necessarily encourage people, you probably see a lot of people walking along texting and tapping as they're walking and typing. One thing we explored here, and this was a very difficult thing to experiment with without getting the participants, putting them in harm's way, is having keyboards that you can see through. So as you're looking at the phone, you're looking at you're playing whatever video content is coming from the camera into the background, and then you're just overlaying a keyboard on top of that. So people can still pay attention to the ground as they're physically walking without necessarily tripping. Not sure I would encourage this, but it's certainly an interesting way to think about how if people are typing and walking, how do you accommodate for that? And then of course on and around device interaction as well. And then face touching and other kinds of stuff like this. And I'll skip all this. An in-car scenario is actually quite interesting because it means you don't have to put in sensors in the car. You just bring a phone and you get all these types of new inputs that become available in the environment. This bit of work that we did here was pre-COVID, but it became more relevant as COVID started kicking in, was looking at what happens when you can't use speech because you're muffled. So, and also what happens when that's just your day-to-day life, you're always going to be having this kind of muffled input. So we tried to use breathing and breath patterns as a way of inputting to the computer. So short inhalations and short exhalations were the way that we did this. So we looked at breathing, speech, the environmental noise, and we took all of that, put it into sort of a small unit. We did some fast Fourier transform analysis, some Z-score thresholding, these peak-to-peak identifications, and then use that to say short patterns would trigger one thing, longer patterns would trigger something else for, let's say, controlling music or podcasts or things like that. And long particular patterns might trigger an emergency response. Not the most elegant type of device, but certainly was an interesting experiment to see if you could actually use breathing as an input pattern. And there's some results there. This is the first time I've given this talk, and I just realized I've got way too many slides, so I'm going to skip ahead. I'm up to 75, and I've got lap. And that's what we did here with Multify. We said, well, if we could track where your wrist was, and if we knew where that bag of pixels were, and we knew where this bag of pixels were, could we merge together and make sure that they were working seamlessly as one unified display space? So that part of it would be for input, for control. Designed and developed this system. The motivation there was, getting your smartphone out can be cumbersome, and it takes time. My colleague, the great actor, and then also these input displays can actually be quite small. So what happens if we could merge the two together? So you'd have a head-mounted display, and you'd look at a wrist, and the two displays would merge into one. As Apple are starting to advance their Vision Pro, we're going to see something like this emerge. We're going to see a merger between that headset and smart devices and the wrist-worn device. And we know this is the kind of direction that they're thinking of traveling. to actually make it one unified experience, because they have the phone, they have the smartwatch, and now they've got the headset, so they're going to merge the three of them together. One of the simplest ones we did was this kind of device aligned, where you would use one input for, let's say, the keyboard, and the second input for just showing you the output. So rather than putting all the content on one display or the other, you actually put half on one and half on the other. And you can see here it's kind of jumping around, because this is, it's a research prototype. This is actually how we had to build it, with this type of tracking to actually make it work. We also had it so that they were split, so that you might control on the wrist, and you might actually see the output in the head, and they wouldn't actually be aligned in one. And the other one is that you would actually really try to merge them. So, like say a map, you might have say a very low resolution map in the head-mounted display, but then you'd actually have a very high resolution content picker on the wristwatch or on the phone, and you'd merge the two together, or things like this. So we're getting on to some of the more interesting ones, or more fun ones. This is a good example of repurposing a sensor. So this is an EOG sensor that are in some of these smart glasses, and they're designed for tracking where the eyes are going to be. But what we discovered is that actually we didn't just have to track the eyes, we could actually also track how you were interacting with your face. So the very coarse-grained gestures like, flicking or pushing or scratching your face or manipulating your face, and all of that could become an input to the system. Interestingly, this got picked up by Canadian TV. Does anyone want to guess what the Canadian television guessed that this was a perfect example for perfect use case people could use this for? In bars, what would you use this for? Tinder, swipe left, swipe right. So you can just imagine at nighttime in the bar, people just swiping on their nose. It might not be great. And then other types of inputs there, rubbing. It's all quite simple, but it actually all does work. And here you can just see like how you might use it when you're controlling music. Not recommended checking your email. What's very interesting when you do these they seem ridiculous, but then you show them to somebody and they say, oh, but in this particular context where you can't actually do something, where you don't want somebody touching their face, let's say in a medical context, this is really useful to keep track of that, to know what people are doing with these glasses, to actually warn them that they're touching their faces. So it turns from something silly into something being quite useful and quite profound all of a sudden. We also actually discovered that the sensing was so good, we could even take the glasses off and place them in the physical environment and actually just gesture above them, and we could actually recognize just the hand moving in close proximity to the glasses. And even with that, you'd actually be able to recognize some simple gestures. So just imagine your glasses just become another form of gestural input that you'd actually have around you. I do want to show this one. This is kind of a crazy bit of work. The episthener. So the episthener is the back of the hand, the back of your hand that you can see in front of you. Now, if you imagine you were a camera that could see that, like what can you see on the back of the hand moving? Well, you can see different things like the skin deforming, you can see bone movement, you can see tendon movement, or you can even see the web of veins all moving. Now, how would you get a camera to have that type of viewpoint? Well, imagine one was built into a smartwatch, as they're now starting to get produced, and that smartwatch actually had a field of view of the back of the hand, and that's what we actually tried to design. So we implemented it as a prototype. This is the first version. I'll show you another version in a second. We then experimented with using it to detect sign language. What you're actually seeing in the top there is that's the image. Okay, that's the image you get off of this very oblique camera view of the back of the hand. It's not something that's easy to process, so you do need to think a little bit about how you're going to do it. And in this case, it was using some fairly simple, at the time, fairly simple AI techniques. We're using different types of convolutional networks. The whole thing is called an inception network with its feedbacks and multiple processing channels to actually determine it, and then using a softmax layer at the end to determine which particular gesture. There's some details in the paper if you want to have a look at it. Again, this kind of confusion matrix to see which gestures are being recognized and which ones aren't being recognized, and the accuracy. What you're basically getting is this camera image, processing it, passing it through these different neural network layers to recognize it. But what we're also doing is we're looking at it, the motion vectors and the images at the same time. So then you can actually start recognizing these different gestures. So you can start seeing these are the different sign languages, gestures for like 1, 2, 3, 4, we're just using the camera image just at that angle to actually recognize all this. This is the very first one. I'll show you the follow-up study that we did in a second. Then using it for detecting hand motion. So even as the hand is moving, you can actually still recognize this. Okay, let me jump on to the more recent one. So we experimented with the basic one here. We then took this and we did a more advanced study using this dorsal net, which is a different type of AI technique, but also looking at different types of motion history. We built a better hardware prototype with the RGB camera, but again, the camera view is just the back of the hand. All you're seeing is the hand. So what we then tried to do is to say, well, let's show what the output, let's see what does the dorsal net actually think the hand is currently doing. Find simple gestures, but full hand motion. So this image you see on the far right, that's what the hand currently looks like based on what the back of the hand is currently doing. So here you can see on the left, that's real video. On the bottom right, that's real video coming from the camera. In the top right, that's what we are guessing the hand is currently doing. That's what our model is predicting the hand is currently doing, which means we can then use it to actually start recognizing how people are playing the piano, which fingers are actually moving. And you can see the hand deforming there, and it's actually been trained to recognize it. So there's a keyboard being recognized. One of the most interesting uses of this is coming up in a second, where not only are we able to recognize what the fingers are doing, we can now actually train it to recognize what objects you're grasping. So if you pick up a mug, if you pick up a container, if you pick up a phone, particular objects, we can train, so suddenly we know not just what your finger's doing, we also know what kind of object your hand is actually grasping, and then using that to drive different forms of interaction. So here we're using it for selecting a clock, virtual keyboards, or even having, let's say, virtual mice, where you're just moving your hands in space. You're not actually interacting with the physical mouse. And Rob did say I could go over time, so hopefully that was not a lie. Somebody was showing a one-handed keyboard yesterday, so I just wanted to show you one of the things that we did on one-handed keyboards, because I thought this might be interesting. This was called shape writing in motion. So just curious, how many, if you have a mobile device, how many of you use gesture keyboards where you swipe your fingers? Wow. Very high. Gosh, that's not the normal response to that question, I can tell you when I ask. It's usually like 10%. That's like 60% of you. So here we thought, well, what happens if the other hand was occupied? So let's say you didn't have another hand, or the other hand was holding, let's say, a rail. Maybe you just use your thumb to do the gesture. What happens if the device was too big, you couldn't use your thumb? So what we tried to do is just have basically a roller ball. So you would just roll the ball around the screen, and that would be basically the gesture for doing this input. And then you just tap with the side of your thumb to see. And people get quite good at this. People get quite fast at being able to actually do this. This inspired people, us and others, to actually explore what happens if it's not a phone. What happens if you actually want to do this, and you have the IMU to do the input, but you don't have the screen? What other types of inputs and other types of devices would you might actually do this with? And that's where we got to rotoswipe. And rotoswipe was just a smart ring that you would wear, where you would actually have it at the side of your arm, sorry, the side of your body at 90 degrees or up high. And then we were just recognizing, could actually people use the rotoswipe input for doing gesture keyboard input? So they would imagine the keyboard and they would just gesture using the ring input to give text. Again, not that high input rate, but certainly people can actually get quite good at it. The reason I mention this one is the first author is now in Meta, and any of these types of novel interactions you start to see in VR is coming from some of this early work that people have tried to do. You know, how do you actually input when you don't have a physical keyboard in front of you, but yet you want to take a text input? And we did different experiments with this one to see how good or bad people were doing it. I wasn't going to actually show it, but I saw somebody was doing one-handed keyboard yesterday, so I wanted to. The last thing I want to show is this, because this is some of the work that we are still continuing. And for any of you who are interested in, we've got as far as this point, and this is pretty good, this far into the talk, and I haven't mentioned large language models. So I'll now mention large language models, and you can't go to a conference these days without hearing about them. And there's a very interesting company called Archetype AI, and the people who developed this work when they were in Google ATAP are now bringing their their type of physical digital large language models in archetype AI, and that's just become available in the last month. So if you're interested in this type, if you like any of this type of sensing, you think you've got a use case for it, have a look at archetype AI, especially their LLM version of it, because it's quite powerful. Anyway, we got access to this way back when in the Alpha Developer Program from Google, and it was radar plus categorization. This type of radar, but not at this scale. Certainly not this type of use case. Definitely not this type of use case. This type of use case. Very, very small radar. Now, the folks in Google, they tried a long time. Like, they put it into the Pixel phone. It lasted for a while, then it didn't. They tried to put it into smartwatches. It didn't last very long. So it hasn't yet gotten into the market as a sort of a standard form. It's in the automotive space. Almost anyone who has a car probably has a radar detector in it, or sorry, a radar sensor in it for detecting proximity. There's lots and lots of radar in use out there, but not necessarily for human-computer interaction. So here they were doing this FMCW type of radar. It's monostatic, so everything is in one very small form factor, receivers and transmitters together, and it has 8 channels with 2 transmitters and 4 receivers for the information coming back. This is one of the scenarios they had, that they were going to have radar information. Now, what's nice about radar, what's not nice about some of the other stuff that we showed you is people don't like cameras being around them. People don't like having cameras in their face tracking what they're actually doing, be it face up, face down, 360 cameras. People are adverse to having cameras pointing at them 24/7 a day. Radar doesn't have that problem. Radar has a very different characteristic signal that it gets back. It's not easy to pull apart and recognize humans from it. When Google invented this originally, nearly 10 years ago now, this is what they were imagining it to be used for doing in-air gestures at a distance. So I could have like picking gestures. That means I could have virtual buttons in the air. I could have dials in the air. I could have sliders and trackpads, all these types of interactions. When they released it to the developer community, different people tried different things with it. This was shown at Google I/O in 2016. These are some of the different use cases people tried it, but this is what we did with it. We did object recognition with it. And we were the first group to actually do this, and a lot of people have done follow-up work since then, recognizing different types of materials. And since then, we've used it for doing pollution detection, for doing threat detection, object detection, gesture interaction, and then physical environment interaction, as I'll show you in a moment. And again, you can see here, the radar system is predicting different types of materials that are being placed onto it, different types of liquids. We tried different whiskies versus pollutants versus other things. There's all kinds of things you can try this with. What's normally used for is this. Like, this is the radar characteristic. This is the signal that you're actually getting with gestures. But what we discovered is, as soon as you place an object on it, the return signal stabilizes. That stable pattern is what we're actually training against. The front, the back of different objects, and you can actually train against it. What's happening with radar? Okay, I've got time. What's happening with radar is the energy is emitted, it hits the object and returns. Not quite that simple. What's actually happening is the energy hits the object. Some of it gets immediately reflected, like light against a mirror, but actually some of it gets absorbed into the object, gets scattered through the object, and then gets reflected. Some of the energy passes through the object, transmit out the other side of the object, and is then lost to the environment, or potentially even reflects back through the material again. And what you end up dealing with are these very noisy signal patterns that you can then put into radar frame bins and then classify against. So what you do, as you do in many of these machine learning systems, is you initially collect data. You then extract your features, you label, and in our case, we were getting about 661 features. And these are just the different bins that you're actually breaking the signal up into per channel. So you get 512 of those bins. And then you can also look for global maxima, global minima, averages, root mean squared, other types of measures, and you get about 600 features that you're actually training on. We built a classifier. We tried all kinds of different classifiers, and we settled on a random forest classifier, which is a very simple type of classification technique. Then you do the same thing again. You pass other data back through the system, and you actually recognize the object, and then you drive applications based on that. You're getting very messy raw signals, but it's actually quite interesting. Even just visually observing something like aluminium versus steel, you can actually see different physical characteristics just in those two return profiles, just without even actually thinking about what the random forest classifier is actually doing. Again, experiments, different day-to-day objects, different types of plastics, different body parts. What's quite interesting in this is, I mean, you could imagine that the material composition of these are quite different, and you can imagine the different parts of the body, have different bone structures and different types of fat and different types of skin thicknesses. But then you get to plastics, and there's a difference here because these are different thicknesses of plastic. These are different types of plastic, but these ones in here, these are just different colors. Same thickness, same material property, but different color. What is causing the radar signal to change? And this was very curious to us, and we ended up going to our colleagues in physics to talk about radar properties. What ends up happening is the different dyes that are in the different colors are affecting the rotational characteristics, because radar isn't just a simple wave, it also has a rotational element to it. And because of the different types of chemicals that are involved in different dyes, it speeds up or slows down to a different degree how the radar is actually passing through the object, which then affects how it's reflected and then returned back. And that was a very curious discovery that we actually made in this whole process as to what were we actually getting when we were sensing it. There's the experiment, picking it up. 10 minutes, good. Same thing, confusion matrices, you see these. And where things are getting confused are things like book versus wood, because they've got some sort of similar properties, different types of objects. Or let's say aluminium versus external hard drives versus scales. They're getting confused with one another. We did different body parts. One of the interesting ones here was, I did this when we lived in Scotland, was that people often try to use these interfaces when their hands are gloved versus ungloved. So could we actually detect where somebody's hand was gloved versus ungloved and then adapt the interface accordingly, or determining whether it was the left hand versus the right hand? And again, it's not pretty because we just had to take the hardware kit that we had and then kind of bootstrap it onto the back of a device. But you could imagine in the future it's built in, and then with the Pixel phone, eventually it did get built in. Same thing, experiments with body parts, forearms, belly, calf, and then using different frequencies. One of the example applications here was just, in a shopping center. This is one of the use cases that actually has now started getting sort of commercial interest, where scales may actually start having these types of radar sensors built into them, because middle-class theft of expensive objects in supermarkets is very big. People putting down, it's a bag of apples, but it's actually a bag of oysters and whatever. So we were using it to actually recognize these things. That's one. Another one was using it to recognize the body parts. And these were students, I warn you up front. So of course, recognizing your hand, recognizing it's in a glove, changing the interface accordingly, placing it at different points on the body, recognizing that. And then, of course, the very important one if you're a student, not this one, the next one. Uber Eats. Yeah, okay. Anyway, and actually what's interesting is early on, we thought about maybe you could use this for doing automatic waste sorting, assisting the blind, self-checkouts, smart kitchens, chemical labs. Representatives from all of these companies approached us in the preceding 5 years after we did this work. And we had a patent, and then the university licensed it out. And the self-checkout one is the one that's now actually progressing to sort of commercial systems that you'll actually see. We did follow-up work where we actually used it for counting. So the system was so sensitive we could actually count the number of cards. So this, of course, was the scenario that you actually might have, let's say, in a casino. But also then recognizing particular tokens that you actually might place onto it, or just determining the amount of sand in an hourglass and actually using that for doing control. And here what we wanted to do was just have different types of tangible interaction. I'll skip over this one. I'm going to end on the more recent work. Skip to you here. Okay, so when we did the original work with the phone, one of the scenarios we had was, well, if this can actually start recognizing the material that the phone is in proximity to, what happens if the radar sensor isn't in the phone? What happens if it's in other places in the environment? So what we did was we put it inside of a shoe. And then we started to actually see, could we classify the different types of surfaces, the different types of motion, whether or not people were walking up or downstairs. One of the big motivations here was for health and safety in physical environments. So knowing where your feet are and then keeping track of that and actually giving people warnings if they're standing on, let's say, a slippery surface, for example. So we built this as a hardware prototype. We built it into a shoe, and then we ran the experiments with the actual real shoes with people walking around the physical environments. What you're actually getting is, as you have in the other scenario, you're getting the energy being emitted, some of it getting absorbed into the physical surface, and then some of it actually getting reflected back. What's interesting there, you also have a time differential, so the energy gets transmitted down, and then it returns back to the receiving unit at a slight different time. And you've also got the velocity of the signal through the air. Here we were just looking at multiple surfaces, so you might have carpet on top of wood, on top of stone, things like this, or let's say rubber mats in between, or even just outdoor physical surfaces like mud and grass and things like that. And this is the radar characteristic that you actually get. So it's a very messy signal. It doesn't look like there's actually a lot there. So the same thing, you have to train a system to actually be able to recognize that and sort of pull it apart and to be able to understand the different components to it. So I think I'm kind of nearly at time. I just wanted to sort of give you some examples of some of the intelligent interfaces that we've actually tried to build, and just try to encourage you to think about, if you are presented with new devices and they have sensing capabilities that's doing something for A, can you repurpose it to do something different or to do an extra value add for users in the environment? Because I really believe new forms of sensing opens up all kinds of new interactions and allows us to interact with the environment in different ways. And that's it for me. Thank you very much.